guys, welcome back to another Physics in the Flesh episode on gravitational fields, orbits. The region of the solar system between Mars and Jupiter, called the Asteroid Belt, contains many asteroids that orbit the Sun. Consider an asteroid in a circular orbit of radius 5.05 times 10 to the 11 meters. A. Calculate the speed of the asteroid around the Sun, and B. Calculate the period of the orbit in years. So let's start off with a picture. So let's say this is the Sun here. You've got the asteroid and it's orbiting the Sun in a circular motion. And in this case, it really doesn't matter what that object is. We've got an asteroid in this case. It didn't have to be an asteroid. It's just some other object. We've got this, the mass of the Sun. We'll call this MA for our mass of the asteroid. And there's a certain distance between them, which we'll call R. Okay, and we're told that R in this case is 5.05 times 10 to the 11 meters. So in order to calculate the speed, the first thing you have to understand logically is that the speed is caused by the force of gravity. And because the force of gravity is pointing inwards for the asteroid, it's also causing the object to move in a circle. So in other words, there's a centripetal force acting on the asteroid. And the centripetal force in this case is the force of gravity. Now, I would strongly encourage you to understand how the derivation of this formula works. Simply memorizing it and plugging it in will not show that you understand the physics. Okay, so always start from the first step. What do you know what's going on? I know that my force of gravity in this case is causing a centripetal force, right? Now, my force of gravity, the universal equation for gravity is G. Now, in this case, I've got two masses. Mass of the Sun, mass of the asteroid, divided by the distance between them squared. And for centripetal force, the formula is mass times speed squared over R. Now, the mass in question here is the mass of the object undergoing the centripetal force, which in this case is MA. Okay, so you set those two formulas equal to each other, and then you start to see that there's a lot of stuff that simplifies. For example, the MA's cancel, and one of the R's cancel. This one R cancels out with one of the R's on this side. Okay, leaving you with an exponent of 1. Okay, so if you were to solve for speed, check it out. You've already got speed by itself on this side. It's only being squared. So you take the square root of both sides and you solve for V. V is equal to the square root of G, mass of the Sun, divided by R. So that's where the equation comes from. I really, again, strongly encourage you, don't start from this. If you start from this and understand why it is, you'll have a better footing and for better ground for solving many, many other physics problems. So I've got my formula for speed. Now I'm going to go ahead and plug in my numbers. So V is equal to the square root of G, 6.67 times 10 to the minus 11, Newton meters squared per kilogram squared, times the mass of the Sun. Again, this is something you need to look up. 1.99 times 10 to the 30 kilograms, divided by R. Okay, the distance between the two centers, 5.05 times 10 to the 11 meters. Okay, so the only thing here is to make sure you don't make a mistake punching this in your calculator. When you do calculate all this and you take the square root, you're going to get that the speed is 1.62 times 10 to the 4 meters per second. So that is the speed of the asteroid going around the Sun. That's pretty fast. Okay, so there's the answer for part A. Now for part B, calculate the period of the orbit in years. So the beautiful thing is we actually already found the speed. So finding the period is going to be actually not so bad. Now, again, I'm going to say the same thing for finding the period. Period means the amount of time it takes for an object to complete one cycle. So in order to solve this, you want to think back to the original kinematics formulas, and that is that speed is equal to distance over time, probably the first formula you learned in physics. Okay, we know what the speed is. We're looking for time, but not time specifically. We're looking for a period, the amount of time to complete one cycle, one circular orbit around the Sun. So that's represented by capital T, the period. Delta D, the distance, is going to be the total distance it goes as it orbits the Sun once. But look at this, it's going around the Sun in a circle, and that circle has radius R. The distance you travel in a circle is called the circumference. Okay, so the speed is actually going to be equal to the circumference divided by the period. So to rearrange this for a period, T comes here, V goes on the bottom, and circumference of a circle is 2 pi R. Okay, so there's your formula for the period. So at this point, you just have to plug in your values. So 2 pi times the radius, 5.05 times 10 to the 11 meters divided by the speed, which we just calculated, 1.62 times 10 to the 4 meters per second. So when you crunch that out, you're going to get that t is 1.959 times 10 to the 8 seconds. Of course, it's going to be a huge number, right? This thing is orbiting at a huge distance from the sun. It's going to take a very long time to orbit. And this number is given in seconds. So let's give it in a unit that's more meaningful, that's more feasible. Okay, so what I'm going to do is multiply this number by 1. Okay, but my 1 is going to be represented by an empty blank fraction. And essentially all it is, it's going to be, you know what, I'm trying to get rid of the unit for seconds, so I'm going to put 1 second in the denominator. Well, not 1 second actually. I'm going to put seconds in the denominator, and I'm trying to get the unit of years out, so I'm going to put 1 year in the numerator. It's always the thing that has the larger unit that you put 1 of. Now, you ask yourself, what ratio of years to seconds equals 1? Well, you ask yourself then, how many seconds are in a year? Well, there's 60 seconds in a minute times 60 minutes in an hour times 24 hours a day times 365 days a year. And when you do that calculation, you end up with 3.1536 times 10 to the 7 seconds. Okay, so let's do it like this. 3.1536 times 10 to the 7 seconds. So sorry, it got a little messy there. 3.1536 times 10 to the 7 seconds. And the reason we do that is because, check it out, the seconds are going to cancel. You're going to get the unit of years out. So the only mathematical step you need to take is 1.959 times 10 to the 8 divided by 3.1536 times 10 to the 7. And when you do that, you are going to get t is equal to 6.21 years. So there you go, a much more feasible answer. And there's the answer for part B. So I hope you guys enjoyed the video. Be sure to smash that like button if you did. And other than that, guys, I hope you enjoy your weekend. Stay tuned next week for video 148, Orbits 2, to be posted Monday at 12 noon. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Woo-hoo! Holy crap, my nose looks big on camera. I gotta find a new angle.